that gated systems, and that's going to be UV visible spectroscopy. And so this is kind of it's an analytical technique, so something that's used in industry all the time, in research for kind of determining what something is, and kind of just, if you have a mixture, like what proportions you have of what, that sort of thing. So it's used in analytical chemistry. And when we are considering UV visible spectroscopy, this is essentially a technique in which we are taking some electrons in some energy level, zapping them with UV or visible light. One of the electrons gets promoted up to a higher energy level, where that change in energy is it's proportional to the energy of the light, right? Actually, it would be equal to the energy of the light, not proportional. So whatever kind of energy that photon had, that's the energy gap between the two kind of orbital states there. And so we're going to take advantage of this by understanding that with our conjugated systems, we had all those orbitals. Remember, say if we had 4 pi electrons, we had 4 different molecular orbitals, right? And actually, I'm going to draw this a little bit farther apart. And remember, we saw that we put the 2 of them in the lower energy orbitals with 6 pi electrons. We have 6 orbitals, and we were able to fill them all in the lower 3, right? We talked about this stuff. What's important to note that, however, if we are promoting an electron from the HOMO to the LUMO using UV light, it's important to know that if we have more orbitals, a greater number of orbitals, the energy gap actually gets smaller. And so if your energy is getting smaller, what does that mean about the wavelength of light? Who remembers that? Wavelength and all this stuff. Opposite, unfortunately. Yep. Long wavelength is going to be our lower energy here. So that means that this kind of lower one, this will have a higher, or a longer, let's say, wavelength. And when we're talking about a conjugated system, we're actually going to be talking about kind of where the molecule absorbs the most energy. And we call this lambda max. And this is going to be the wavelength that gets absorbed the most. So as you're shining your light on your molecule, it will absorb a whole different array of lights for different orbitals, but we're going to see that one particular one we're focused on will be lambda max, which is the kind of where it absorbs the most light. And this is something like, you've talked about with doing spectrophotometry way back when, in 101, right? You did Beer's law and all that fun stuff. We're going to see with conjugated systems, the more kind of conjugation we have, we're going to get longer and longer wavelengths. And so as a result, those are going to stretch from the UV range into the visible light range. And so as a result, you see that color in nature often comes from having many conjugated double bonds. Like, beta carotene, for example, has a ton of double bonds. And to us, we see it as bright, bright orange. And so we see that as we add more conjugation, let's see how to write this. As conjugation goes up, the lambda max gets longer and can go into the visible light range, meaning it's going to be absorbing light in the visible spectrum. And remember, once something absorbs light in the visible spectrum, then we can see it as having a color. So beta carotene, which is bright orange to us, makes carrots orange, right? That arises because the blue light of the ultraviolet spectrum is being absorbed. Remember in 102 you talked about a color wheel and you had all the like opposite colors. Suffice it to say, I'm not going to test you on that. That's not important here. The point though is that we are adding more conjugation. We're squishing these orbitals closer and closer together in terms of energy. Therefore, we need less and less energy to get them to promote to a higher orbital. And then your lambda max will get longer and longer, eventually coming into the visible spectrum. So that's kind of where color comes from with a lot of compounds. So that's that. For example, some colorful compounds that you might see. This is one that I think you might be doing in lab. This is dibenzyl acetone. We can see here we have quite a bit of conjugation. This thing is bright yellow. Because you see how much conjugation it's got here. We've got all these double bonds alternating with each other. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 double bonds, which means 18 pi electrons, which means we have 18 orbitals, and think of how close those are going to get together. So this thing is bright yellow. Something you'll synthesize in, well, you would have synthesized in lab had we really been there. But you'll watch either me or Chalmers do a video of making this. So bright kind of yellow orange. And so that's, again, it's kind of colorful because it has all this conjugation. Alrighty, but we're going to see we have rules for kind of predicting lambda max. And so with these rules, we're going to see, we're going to have, I think, 5 of them. And these are called the Woodward-Pfizer rules. I will put that here. You do not need to know that. Those are the scientists who came up with these things. So first thing is it's kind of going to give us a formula for how to predict the lambda max of a molecule that's got conjugation in it. And the first one is we're going to have our base value of 217 nanometers for just having a diene, a conjugated diene. So as soon as we have one diene on there in a molecule, we'll have a lambda max of 217. So this butadiene here would have that lambda max. Very exciting, right? Let's go ahead and throw more double bonds on. We're going to see each additional conjugated double bond gives us plus 30 nanometers. So every time we add an additional conjugated bond, we're looking at another 30. So this one we would expect to be at 247, right? We would expect 247 for this one. Or if we were to say, let's instead have as long as they're conjugated, so that means they're alternating, right? So for this one, the lambda max, we would expect it to be 277 nanometers. So still in the ultraviolet range, but we see here we're getting more and more. It's important to know we have some other terminology to put here. kind of the conjugated part of our molecule is going to be called the chromophore, and everything else we're going to see are going to be oxochromes, but we'll see an example of that in just a bit, but I want to give this to us as our next kind of formula here. So it's called an oxochrome. So that means it's sticking out of our conjugated system. So if we throw some methyl groups on here, those are oxochromes. I can go ahead and do this. So this part of the molecule here, we call the chromophore. So it's where the kind of color is coming from. Chromo means color in Greek, Latin, I think it's Greek. And the other bits here that are not conjugated, that are just kind of existing, those are called oxochromes. So they're auxiliaries. They're just kind of extra stuff. And so we're going to see that each oxochrome alkyl group, oh my gosh, that's the worst spelling ever, group, is going to give us plus 5 nanometers. So if we have now those two methyl groups on there, it's now going to become 287. So we're still going to have now our 4 double bonds conjugated together, and now we've added 2 alkyl groups onto it. Each alkyl group gives you 5 nanometers. So really we're going to see that this kind of predicting lambda max is just a function of looking at your molecule and figuring out what you're looking at. And we have kind of 2 more possible additions to this. And so I think we're lucky. Mrs. O tends to go crazy and has like 10 different rules. You know, here's one with nitrogen, here's one with chlorine, whatever. Forget it. I'm not going to go too crazy on those because it's less important. If you really do end up taking or going into this sort of field of chemistry, you'll definitely take many analytical chemistry courses where you'll actually talk about more specific things on this. But even so, predicting it is kind of, it's a, computers do it for us better. So suffice it to say, we'll just give you a basic knowledge here. So, okay, we have now, the next one is, an exocyclic double bond. So exocyclic means you're going to have some sort of ring, and you have a bond, a double bond that is not entirely contained within the ring. So we have, if you can see here, that cyclohexane that I've drawn terribly, we have one double bond within the ring, and we have one kind of exocyclic double bond. That's going to give us another 5 nanometers. And so we're going to see that kind of one position has to be touching the ring for an exocyclic double bond, like it's touching there. I'll draw that. So we have kind of a vinyl ring, and then we have that one's not in a ring then. So this one's on the ring. That one's not on the ring. All right, and so this is in addition. So if we were to kind of look at lambda max, okay, well, we have got 217 as our base value. We have one exocyclic double bond. I'll do these in different colors, maybe. What did I do with the other ones? Purple, okay. Note, though, we do have 2 alkyl groups coming off of this diene. So don't forget the other ones. These are still going to be oxochromes. So every point that your oxochromes connect to your molecule, that's when we're going to be adding those 5 for that. So we're going to add 10 nanometers for those 2 oxochromes. We'll have another 5 from the exocyclic double bond, and then we'll have our base value. So it's going to be 217 plus 15, which gives us 232. So that was 217 plus 10 plus 5. For this, I will use green for our exocyclic double bond. Hold on 1 sec, I can't hear. Okay, say that again, sorry?
Can you go over the calculations again real quick?
Of course, of course. So, relax, buddy. Okay, so I'm going to go ahead and kind of color code everything here. So, our main conjugated double bond, that's what we always start with for this. So we're always going to start at 217 for having a conjugated system of any type. So, with this molecule here, we have our base value, which is 217 nanometers. We then want to look, do we have additional conjugated double bonds? We do not, we only have the 2. So we start with 2 always. Every additional one we add on, that's adding 30 nanometers. Since we don't have any of those in this molecule, we're going to skip down. We're going to see, okay, how many other alkyl groups do we have? Other carbons that are not double bonded and are not participating in our kind of conjugation. I've circled those 2 carbons in purple here. So every carbon that sticks out of your conjugated line is going to be one of these alkyl groups. So even though it's in a ring like this, you're still going to have 2 of them. So we have alkyl groups. We have 2 times 5 nanometers. And I'm just going to kind of keep our... Oops, that was not the right... And then we've got exocyclic, oh my gosh, exocyclic double bonds. We have 1 of those at 5 nanometers. That's going to give us 5 nanometers. If we add all these up, it's 232 nanometers. So that's how I've calculated it for this one. So I'm going to be consistent as we go through. I'm going to put our alkyl our oxochromes in purple, our exocyclic bonds in green, and I'll do extra conjugation in blue. We'll do a couple of examples here as well as we go through. And let's see, do I have room for the last one? Okay, so we have one last one, which we will call a homoannular diene. More vocab words here. So this means that we have 2 double bonds in one ring locked in S-cis it's locked as S-cis. I'm going to move this somewhere else. I'm going to just move this down a little bit. Okay, and I'll copy the molecule so we still have that here. Oh, relax, baby. Okay, so I'm going to just copy this. Actually, let me put it here. Okay, so this will give us 39 nanometers. And what this looks like, it's ugly. And we're looking at this. We're looking at a pair of double bonds that are located within one ring, and they are locked in an S-cis conformation. So we see here in this cyclohexadiene with the extra cyclohexane on it, we've got the 2 double bonds stuck in a ring, locked therefore in S6. That's going to give us an additional 39. And we'll do this one in orange, I guess. So we have now our orange diene. If we want to do the calculations for this, I'm going to move it down actually. If we move this one down, and we want to do our calculations, we can do that. We've got our base value of 217. I'll stay on this part just for 30 seconds or so you can make sure you get that. So homoannular dienes, they're stuck in one ring and stuck as S-cis. So, cool. Let's go ahead and try and figure out lambda max for this guy. So, we've already got our base value. Next, we want to look, do we have additional conjugation on this? Nope, we just have the two double bonds, so no more conjugation. Let's look at oxochromes. Do we have other alkyl groups that are sticking on this molecule? We do. Oxochromes I'm doing in purple. So let's go ahead and look at the molecule and look at every carbon that is sticking off of our diene or our conjugated bit. There's one, there's one, there's one, there's one. Do we see how we have four oxochrome alkyl groups here? So we have four carbons that are kind of connected to our conjugated double bond system. So we're looking at all carbons that are touching a double bond, that are not participating in the double bond. And so in this case, we have four of those. Each one is worth 5 nanometers. So that gives us plus 20. Our base value is 217. Next, we're looking, do we have any exocyclic double bonds, ones that are sticking out of a ring? Nope, I do not see any double bonds that are sticking out of a ring here. And then do we have a homoannular diene? Yes, we do. We have two double bonds locked in cis conformation within a ring, a single ring, and so we're going to have that here. So we're going to add 39 nanometers. Okay, so the reason we don't count those two carbons on the right side, you mean these two, yeah? Like these ones? Okay, because those ones aren't connected directly to the double bonds. We only look at ones that are right adjacent to them. Yeah, so those are farther apart, so we don't worry about them. Okay, oh gosh, I have to actually add now. Aha, calculator. Okay. 217 plus 20 plus 39. I don't trust myself to do this. So that gives us apparently 276 nanometers. Having this one. And that's it. That's all the rules. So we have 5 things. Base value, extra conjugation, alkyl groups, exocyclic bonds, and then the double bonds locked in S-cis in the ring. So let's take a look at some examples. Yeah. Yeah.
So that was how many points?
39 points for that one.
Okay.
Yep. It's a weird number, I know.
Oh, the two of them is 30. Okay.
Yeah. So just having that unit counts as 39. Okay. Let's see, what can we do with this? All right, here we go. And there we go. Okay, here's a molecule. let's predict its lambda max. So whenever we're approaching a problem like this, we are just going to kind of go in order. We can even write them out here. We can say, okay, we've got our base value. We've got extra conjugation, as in additional more than 2 bonds. We have our alkyl groups. We have our exocyclic double bonds. And then we have our homoannular diene bit. So when we're looking at this, of course we have our base value, so we don't even need to think about that. We have a diene, that gives us 217. So remember, we always start with 2 double bonds. That's our base value. If we're looking at extra conjugation, well, we're looking, okay, well, we've got 1, 2, 3, 4 double bonds here, right? That are all conjugated. They're alternating, single and double bonds. So with that, we have 2 more bits. Do we all see how we have 2 extra ones? We start with 2 as our base value. We're going to add extra for every double bond more we have. So we have 2 extra double bonds at 30 each, which will add 60 to our lambda max. So if I chose, here, I'm going to choose these 2 as our extra bits. Those are the 2 extra double bonds. So I'm going to start with the 2 down there on the left, and those other 2 are my extra 2. All right. Let's go ahead and look at extra alkyl groups now, some oxochromes. We're looking at every carbon that's touching a double bond that is not part of our kind of main line here. So we're going to have this one connected to the double bond above. We have this one, which is connected to the double bond above that. We have this bottom one here, which is connected to the double bond on the left. We have this one, which is connected to the double bond on the right. This one connected below. And this one connected to the right. Let's see, am I missing any here? Looking at all my double bonds, looking at everything that's on them. I think we're good there. So we have now 6 of those extra alkyl groups. Each one's worth 5. So we're going to add 30 here. It's a really ugly plus symbol. Let's try that again. Do we have any exocyclic double bonds? We do not. All things that are coming out of the rings are all single bonds, so we have 0 of those. If we did, they would be worth 5. So I'm just going to write plus 0, because we don't have any. And then do we have a homoannular diene in this molecule? We do. That's going to be this part here. And so we are going to add 39 nanometers here. And then finally we can add them all up. So 307 plus 39 is 346 nanometers. So I'm going to do the calculation just in case I'm not so great with these nines. And so the process here is just looking at your molecule, identifying if you've got these 5 things. Do you have a diene? Do you have extra double bonds? Do you have alkyl groups attached to your double bonds? Do you have exocyclic double bonds? And then do you have a kind of locked S-cis bit.
So for the alkyl group one,
Mhm.
you said, so you're counting it, how are you counting those? They're connected to the...
Anything that's connected to a double bond. So you know how we like talk about how substituted a double bond is? That's essentially what we're doing here. So we're looking at any carbons that are not part of our main double bond line, essentially our conjugated line, any alkyl groups that are touching those double bonds. And so if I were to kind of redraw this molecule,
Can you just highlight where the main...
yeah, sure. So let's do that in dark blue. So this is our conjugated line here. So it's following those alternating double single bonds. So that blue part there is our conjugated system, the dark blue. And so we're looking at every carbon that's connected to the dark blue.
Oh, okay, got it.
And then like if we look at the previous one, this was our conjugated system. That was it. So we're just looking at everything connected to those ones. And before that, that was our conjugated system. So, okay, we'll do more. Cool. Okay, let's do one more. Let's see, what shall we do here? How about we do this one? Let's see, how about, yeah. All right, let's do this one now. So actually, I think it might be a good idea to just find our dienes. We can do that first. Right, we can say, okay, well, here's going to be our conjugated line. We have, of course, at least two double bonds here, so we have a base value. So we're going to go to 217 to start. Just going to copy all this stuff. So base value takes care of two double bonds. So do we have any extra double bonds? If I say my base value is, or my base is these two, I get that the dark is a little hard to see against the black, but those are two double bonds, right? So we have one extra one. We have one extra double bond, which is going to give us 30 each. Now we want to go ahead and do those alkyl groups. So everything connected to the dark blue line is what we're looking at here. So we've got these two. We've got this one. We've got, and these last three here. So all the carbons that are connected to our dark blue chain of conjugation. 1, 2, 3, 4, 5, 6 of those. Each of those gives us plus 5, so that's plus 30 from the alkyl groups. Next question is an exocyclic double bond. A double bond that is touching a ring, but is kind of sticking away from it. And indeed, this one here, we're going to have this total crazy colorful thing. That's an exocyclic double bond. Let me just draw it again. This is exocyclic, so it's coming out of your rings. So we have one exocyclic double bond here, a double bond sticking out of a ring. Each exocyclic double bond is 5. We only have one. And then last thing we want to check, do we have any homoannular diene in here locked in S-cis? We do not. I do not see any 2 double bonds within a single ring that are locked in S-cis.
Professor, I have a question.
Yeah, what's up?
So you mentioned how the base value includes 2 double bonds. Would one of the two, can the double bond be an exocyclic double bond?
Yeah, sure, for sure.
Okay.
So I could have said my base is these two, and then the exocyclic one would be my extra conjugation, so that's going to give me plus 30 there, and then it's also exocyclic. And so, it doesn't, all these things are just additive, they're independent of each other. So if in the previous one, I started with the two that happened to be the S-cis double bond, the orange circle. And then I added the extra 2 on afterwards. I could have started with my diene being those top 2 that I've circled in light blue, and had the extra 2 double bonds be the other one. So it doesn't matter what kind of double bonds you have to make your base, as long as they're conjugated. So as long as they're alternating, that's all that matters.
All right, thank you.
All right, so adding this up, 277 plus 5 is 282 nanometers. Hooray. Awesome. So, that's it for the rules. It all just comes down to taking a look at your molecules and doing some kind of counting things. I think it is helpful to color code these sorts of things if you happen to have colored pencils or whatever. It can make things a little bit easier for you. Never mind that you destroy your molecules so much that you can't even see it anymore, but that's okay. Alrighty, any more questions on those before we go on to our next topic? Okay. Cool. In that case, let's go ahead and move on. We're going to now talk about aromatic compounds. So this is going to be actually a super short chapter, which is nice. So last semester you were introduced to benzene. Benzene is something you were told never to react because it doesn't do a lot of the stuff that normal alkenes will do, and that is indeed true. Benzene cannot be, you can't just throw bromine at benzene and hope to brominate some alkenes like you can with regular alkenes. Like, right? You can throw bromine at an alkene, you've now got a brominated alkane. But it doesn't work with benzene. Benzene is special. And we're going to find out why. But first things first, we're going to talk about naming a couple of these things. So we're going to see that we're going to have quite a few substituted benzenes that have special names. Sometimes you'll have some benzenes you'll have that have got low priority groups on them. You'll name them as benzene as your kind of parent name. This one you'll name chlorobenzene. This one's ethylbenzene. And then you've got nitrobenzene here. And so we're good there. Basic groups on a benzene. But we're going to see that some benzenes have special names. And these ones you will need to apply the highest priority parent name. For example, let's go back to black actually. This one is toluene, or sometimes called toluol, but that's kind of a really obscure name. Toluene is typically used. So that's a methyl group sticking out of your benzene. You have phenol, not phenol, phenol, which is your alcohol on a benzene ring. So phenyl alcohol, phenol. If you have an ether, this one is called anisole. If you have an amine, that is aniline. If you have the carboxylic acid, that is benzoic acid. If you have the aldehyde, that is benzaldehyde. And unfortunately, these parent names must all be memorized, so unfortunately, they're just super common. If we have the ketone, that is acetophenone. And then our last one is the double bond, kind of the exit, or just last little double bond there, that's called styrene. So we have 8 parent names that we're going to need to memorize for various benzenes, aromatics. All of these, you'll follow your normal kind of naming rules, right? The priority is, carboxylic acids are the highest priority, and then you'll have, after that, let's see, what do we have here of our options? Actually, I put a whole list in Discord for you guys. Remember, there's a whole list of priority of functional groups. So carboxylic acids first, then we go to amides, and so on and so forth, all the way down. So first step is you'll want to identify your highest priority group on the benzene, and if that one has a special name, then you will use that name. Let's do a couple of examples. With this, alcohol has the higher priority than an alkyl halide. So you will say 2-bromophenol, because you would number this 1 and 2. You could do it this way. Interestingly, we can also call this by another name, O-bromophenol, where the O stands for ortho. We're going to see that if you have di-substituted benzenes, you can talk about their positionality in terms of other names. So we can say this is ortho bromophenol. And that means the same thing as a 1-2 relationship. So something on one carbon, something on an adjacent carbon. On a benzene, if you have 2 things, you can name it ortho if you want. And we're going to see when we talk about reactions using benzene that certain things will, attack ortho positions. And we're going to have 2 other positions that we'll talk about. So relative to this oxygen here, these 2 positions are ortho positions to that. So either one of those. So if our bromine happened to be on the other one, of course it would be the same molecule, right? But we could still call it ortho. So to either side of your main substituent is an ortho position. we've seen another one before. We've seen something very similar to this when we talk about epoxides, right? We see that one of these names is metachlorobenzoic acid. We don't have peroxy this time because I've only got a regular carboxylic acid, but remember MCPBA, metachloroperoxybenzoic acid? That is how we'll name this. The meta part is a 1-3 relationship. Let's do this meta in purple. Why not? The meta position is something at 1 or 3. So here is your main carbon. These are your meta positions. So relative to your carbon of interest, a meta is a 1-3 relationship. So 1, 2, 3. 2 carbons away. So 1 and 3. We could abbreviate this then. M-chlorobenzoic acid. Oh, it is chloro. I thought it was bromo for a sec. Or we could be very good and do our locator numbers. Sorry, 3-chlorobenzoic acid. All right, and the last position we have there I'm out of space, I know. Okay. We're going to see that this position is called para. And then there's a 1-4 relationship, so they're the opposite sides of the benzene. So 1, 2, 3, 4. The para position is the opposite side. And if we were to name this, the amine takes priority, right? So we're going to have para-nitroaniline. Aniline is our parent name because benzene with the amine is called aniline. You call this para-nitroaniline. And we could also say 1,4, no, sorry, not, keep saying both, 4-nitroaniline. That would work. All right, something you've used for your acetaminophen synthesis, 4-aminophenol. We can take a look at this as well, or we could call it para-aminophenol, either way. Still a 1-4 relationship. If we look here, we've got phenol as our parent name. So phenol is the alcohol. And if we've got an amino on position 4, we just need to put that down there. So these are not terrible to name once you've learned the 8 basic ones, I suppose. What else can we do here? So all this ortho meta para stuff you can use for if you have 2 subs only. Only 2 substituents you can use ortho meta para. As soon as you throw on more, you have to use locator numbers instead. So here's another one. Let's talk about this guy. Important molecule. Ooh, that's not a ring at all. There we go. If we were to number this, nitros don't take any priority at all, so alkanes beat that. We're going to see this will be 2, 4, 2, 4, 6, nitrotoluene. So toluene, the methylbenzene, is our parent name. The nitros are substituents. This molecule is TNT, explosive, dynamite, trinitrotoluene, at positions 2, 4, and 6. So position 1 is occupied by our methyl group, because the methyl group has priority. I did put the thing in Discord, right, with the priorities. Let's check real quick. Couldn't find it. I think it's like the first thing I put. Oh, I have to put some new stuff for you. Yes, functional group priorities. So, let's see what we get. So there should be a big old chart here that's going to have it all. Yeah, so carboxylic acids are our first priority. We're going to go down. We're going to see as we go down that, okay, alkenes, who cares about these? So these functional groups down here always are lower priority than just plain old alkanes. So stuff like nitro groups. Nitro is in fact your lowest priority group. You're always going to name nitro as a substituent. And so this is hierarchical. So carboxylic acids are number 1 priority always. Sulfonic acids, we don't really have as much. Esters, acid halides, amides. Talk about those later on, but this is the order. So whatever you hit first will be your suffix, and then everything else after it will be your substituent names. So carboxylic acid number 1, and then we go down the list. Okay, and so we keep going down here. Nitriles, aldehydes, ketones, alcohol. So this is just in Discord. If you go to extra resources, it's the very first post there. So, ta-da, that's where I am, right there. Cool. So that is there. So you may want to review that. So of these, our parent ones, the benzoic acid is our highest priority, carboxylic acid. Then let's see, probably then would be the aldehyde. Benzaldehyde would be our second priority. Then the ketone, then the alcohol, the amine, and then the alkene, I guess. The anisole and toluene are kind of low priority because ethers and alkanes are kind of boring. So, alrighty, let's see. That's the naming part of it. So it's really just learning those new kind of 8 names. So that's just going to take practice. And so if you have more than 2, you're going to have to put locator numbers on things. We can do one more example. Why not? Let's see. Okay. That's ugly. Let me try that one again. Here's one last practice for our nomenclature, and I'll stick the methyl that way because why not? So we have to identify our parent name first. With this, we're looking at our highest priority. If we've forgotten, of these 4 functional groups, aldehyde is the top priority. And so we're going to go back up. Which one of these is the aldehyde? Aha, there it is, benzaldehyde. So benzaldehyde is going to be our parent name. The aldehyde has the highest priority of these 4 functional groups. I'll write that down. So the aldehyde has highest priority, so that means it's going to be the parent name. So that means benzaldehyde is our parent name. So that means that's also going to be position 1. Remember, once you have your kind of your position 1 done, you want the lowest locator numbers possible. So we're going to start numbering then to the left Otherwise, we're going to end up with higher numbers. So these will be our carbons. And so now we just have to name these as normal. We're going to have on carbon 2, we have a methoxy. On carbon 4, we have hydroxy. And on carbon 5, we have fluoro. And so we just need to alphabetize these, so it'll be, I think, the opposite order as I've written them. So we're going to have 5 fluoro, 4 hydroxy, 2 methoxybenzaldehyde. Oh, I tried to fit that in, guys. It didn't work. Okay, we'll fix that. All right, any questions on that one? So, same stuff as before, just naming, not as exciting. All right, let's talk about benzene then. Okay, I'll even draw it with the 3 double bonds. We're going to see that if we try and treat benzene with things we might treat our regular alkenes with, we end up with, here, I forgot my stereochemistry, shame on me. If we try and just treat it like a regular alkene, we get no reaction happening with these. And we're going to see kind of why that is when we look at the molecular orbitals. But suffice it to say that benzene doesn't react like normal alkenes do. And if we go ahead and kind of take a look at something we did before, and we can look at delta H here. If we are going to take some various things, and if we take benzene, if we were to try and heat these, or not heat these, hydrate these, we're going to see that the first two this is about, I think, 240. It might be like 237 or something. Don't need to know these numbers, as always. If we were to try and predict how much benzene would need to react, to be hydrated like this, to reduce it, we might predict around 360. Negative, right? It's excess number. But in reality, though, I have the number here somewhere. In reality, it actually is about negative 208 kilojoules per mole to completely reduce our benzene. And so, just like before we saw that with conjugation giving us some extra stability, this gives us way, way more stability. This gives us roughly 152 kilojoules of stabilization energy. So it takes less energy to react this, or it gives off less energy when we react this, because it has less energy to begin with than we might expect it to have. So that means that benzene has less than we expect it to have. Wow, that's terrible. Expected. And so we're going to see that it's going to be unusually stable. So it's quite a bit lower in energy than we would expect it to based on other similar molecules. And so it's unusually stable. And we have evidence, remember, it doesn't react with normal things that alkenes react with. And so when we actually do this, we observe quite a bit less reaction happening here. And as a result, we're going the scientists who discovered this phenomenon kind of termed it the stability of aromaticity. And that name is kind of silly because, it comes from the fact that many of what we are going to call aromatic compounds have nice smells. They smell nice. And so that was kind of like the old way of determining this was like, oh, how does it smell? Oh, it smells nice. It must be aromatic. We have better definitions now. And in fact, there are many aromatic compounds that do not smell like anything. So we're going to see that aromatics do have better definitions now. In terms of things that smell, aromatics that we might be familiar with, cinnamon is one. So cinnamaldehyde is the primary flavoring and smell compound in cinnamon. And that is this guy. Cinnamaldehyde. So it has that aromatic group. This is trans-cinnamaldehyde, but whatever, that's the more common one. What else do we have? This is methyl salicylate, or oil of wintergreen, as it used to be called. So, like breath mints, that's that. So that super minty smell is an aromatic compound. Cinnamaldehyde is an aromatic compound. A lot of different nice smells are from aromatic compounds. Things that make clothes smell. A lot of primary flavoring or aroma components are aromatic. So that's the old definition. If it smelled nice, it's aromatic. But we're going to see here we have better definitions. So, if we want to think about benzene, we can think about it in terms of molecular orbitals. And this is going to be a little bit different because we're looking at a cyclic system. So we're going to see we have 6 pi electrons in benzene. So we're going to have 6 orbitals, but 2 of them are actually degenerate. Actually, and then their corresponding antibonding orbitals are also degenerate. The reason for this degeneracy is because of the symmetry of the molecule. So that's all you need to know. In fact, you don't even need to know that. Just understand that there are 6 orbitals, and due to symmetry, they're going to have some degeneracy. Degenerate due to symmetry. So remember, degenerate means same energy. So we have some degenerate orbitals here in benzene. Normally, of course, we'll fill them. And so we're going to see that all of these will be lower energy than we would have before. And if we want to kind of take a look at them, if we want to let's see, what's the best way to kind of half-ass this? I only mean that because I want it to be kind of short. This kind of lowest one before is very similar to our hexatriene that had all of them kind of blobbed together like that, right? So if it were linear like that, it would look like this molecule. But imagine now it's just a ring. So instead you have all of these. So we've got our rings. Oh gosh, I've got to put them all here. I hate talking about these molecular orbitals. They're so hard to draw. So our lowest energy one is going to look like this, where we have a complete blob of blue on the top and a blob of green on the bottom. So we have complete overlap on the top, complete overlap on the bottom for our lower one. For the upper, the next higher ones are homos of benzene. We're going to have nodes in them. And we're going to see that one of the nodes we could have, because of the symmetry of the molecule, we could put our node like this, where we have kind of these three overlapping nicely there, and we have the blue ones overlapping nicely over here, and we've got our kind of nodal plane in the middle there. And so we can end up having them split like this. And we'll see the point of all this, don't worry. And so we can end up having our kind of benzene split that way, which ends up giving us kind of, let's see, how am I going to go? This blob here, blob here. I'm terrible at these blobs. You know what? I have a better idea. Let's cheat. Oh, I don't need that right now. Okay. Let's see. I'm going to just show them to you on Google, because why would I not? So let's see, molecular orbitals of benzene. We're going to have so much better images than ones I could ever draw for you guys. So, aha. Okay, I'm going to just go ahead and flip my sharing screen here. Change windows, molecular orbitals of benzene. Okay, here we go. Where are we here? So, oh gosh, some of these are like jankiest old drawings ever. But essentially, let's zoom in here. Okay, apparently I zoomed in too much. Here we go. So if we're looking at the bottom one here, we have our blobs. They're using red and blue. I use blue and green, whatever. This is kind of the one we just drew. And if we just kind of rotate that, we get the other one. So we're going to have these kind of nodal planes. We can have it that way, or we could have it the other way around, horizontally instead, and we end up with our orbitals. The important part that we're looking for here is, it's kind of, the important part is that all of these are below the energy of our original 6p orbitals that might be. Once we combine them into the molecular orbitals, they're all lower energy. So I'm going to switch back here, back to our Discord, or back to my normal screen. Where did it go? There it is. I'm not even going to bother with these other ones because I'm terrible at drawing. Suffice it to say, you get this nice lovely sandwich, which is how you get that lovely resonance of benzene. But the important part here is that our original 6p orbitals are all higher energy than our molecular orbital ones. So all the MOs here are lower energy than the original atomic orbitals. And I'm just going to write here our filled ones, all our bonding ones. That's the important part. And we're going to see, in order for something to be aromatic, one of the conditions that we need it to meet is that all of these orbitals have to have lower energy than their original orbitals. So this is a part of where some of that 152 kilojoules is coming from. So filled orbitals are going to have lower energy than our original ones. Just like with conjugation, we saw that our filled orbitals had lower energy than our original p orbitals. So it's working the same way for aromatic systems. We see here that another characteristic is that aromatics must be cyclic. And we're going to see that. So we see the reason that they have to be cyclic is so that we can have this complete overlap. So previously, with the hexatriene, we had a blob on top and a blob on bottom. Those were kind of stretched out blobs, right? We had previously seen a blob like that and a blob like that, right? That was our hexatriene. With benzene, though, we see it's a nice happier disc than this big old baguette. We have, if we want to think about this in bread terms, as we always do, this is like our happy little boule, our happy small little round loaf, and this is more the baguette. So we're going to see there's a lot better overlap in the more condensed one. I don't know why I'm thinking about bread, but here, we can erase those terms. Let's just say this is kind of much more overlap. Much more overlap here than this one. This has much more overlap than our regular hexatriene that had everything spread out over the entire molecule. With the cyclic structure, they're contained. They can just keep resonating and flowing throughout the ring, and there's no ends to this. So no ends means things keep on cycling through, and so that's kind of our other characteristic. Things must be cyclic. So let's look at other ones. Let's look at, how about this guy? Let's see if this thing is aromatic. Let's find out. First off, we're going to see that if we try and do stuff, let's just see what would happen if we do this. Unfortunately, with this one, we see it does react. So evidence says no. But why? Why does it not? The reason for this is the molecular orbitals are not going to be all lower energy with this particular molecule. If we're going to look at this, if we've got 4 pi electrons, we're going to see that the molecular orbitals that it makes again, we have that one degeneracy because of the symmetry of the molecule. You don't need to know that, by the way. Like, I'm totally cool if you're like, oh, that's right, we have 6 things, 2 of them are degenerate. Don't worry about it. I'll show you simple ways to get through this. Regardless, here, we have these kind of non-bonding they're not all lower energy either. So, as a result, we're going to see that this is not an aromatic compound. For an aromatic compound, we need to be cyclic. We need all of our orbitals to be lower energy, and I might not have stressed this earlier, but everything needs to be filled also. So we don't want kind of lone electrons just chilling by themselves. So we have to have all our orbitals filled as well. And we're going to see that that's why this one is happy to react. It's going to say, oh, bromine's here. I'm going to go chill with bromine. I'm not all happy here in my aromatic system. Here's the big picture, though. If you have 4n plus 2 electrons in a cycle, you're going to be aromatic. If you have 4n electrons in a cycle, you are going to be anti-aromatic. So with this, it's in fact unusually unstable. This cyclobutadiene is unstable. And we're going to see that anything that has 4n electrons in its kind of pi system will be anti-aromatic. So if we have this cyclooctatetraene that has 8 pi electrons, we're definitely going to see that this should not be aromatic, right? It should in fact be anti-aromatic. That's unfortunately, we will have non-aromatic things too. This one is anti-aromatic. So it's going to have 4n electrons. Isn't this a lot easier? Just count the electrons and see. If you have 2, 6, 10, etc., you're going to be aromatic. If you have 4, 8, 12, you're anti-aromatic. It's wonderful. So something like this remember that kind of with resonance you could have lone pairs that resonate and participate in aromaticity, in aromatic things. Not only is this a terrible molecule to begin with, but it's even more unstable than you'd think, because that now has 4 pi electrons. Remember that those electrons there can participate with resonance, right? They can get in there. This will also be anti-aromatic. And so it's not a good thing. We have 4 pi electrons that are interacting here that are not good. They're not going to be working out nicely. However, there are also other aromatic ones that are not benzene. If you have pyrrole, we don't need to memorize that structure, but note when pyrrole resonates, it can resonate those electrons in, right? The electrons can resonate in, and therefore they participate in the pi system, and so we can count those as part of it. If we do resonate this, of course, we end up with, what would we end up with here? And we would have a lone pair here. And that can just go back in and do all sorts of fun stuff. But the point is now, we're still having 6 pi electrons here. We have 2 from the pi bonds, we have 2 from the lone pair on the nitrogen. And so as a result, we see that this will be aromatic. These pi electrons that are in an sp3 nitrogen can interact. Remember that electrons in an sp3 lone pair can participate in aromaticity. if you look at, say, this one, this would also be aromatic, because those pi electrons, those lone pairs can push themselves into the system, and you can resonate them around. If you can do resonance with a pair of electrons, that means that you can count them as part of your pi system. So we have 6 pi electrons here, which is 4n plus 2, which is aromatic. All right, so we can keep doing stuff. Sometimes though, like if you have heteroatoms, they might not be aromatic, or they might just not do anything at all. If you have pyridine, I mean, it's certainly aromatic already. Actually, I shouldn't say that. This lone pair, if we try to resonate it, let's see what happens. If we try to resonate this, we're going to get something really weird. We can't, by the way. We're not going to be able to resonate these in here. But if we tried to, for example, do something weird like this, we could try. The reason that you can't resonate these in, by the way, is because of the geometry. You now have some like weird accumulated double bond on the nitrogen. That needs to therefore be 180 degrees apart, sp hybridized. Not going to work. You have got this lone pair here. You've got this weird stuff happening. It's not going to work. So you can't resonate this because of this thing here. You're not going to end up doing that. So that can't resonate. So you're not going to count those lone pairs as part of your pi system. Pyridine is aromatic already. We're okay with that. Those electrons don't contribute to the resonance. They can't go in there. They're also on an sp2 nitrogen, so that's your hint. So they're on an sp2 center already, so that means that those electrons are in an sp2 bond, which are pointing away from the system anyway, so there's no way they can even overlap to begin with. Not only are they get this like nasty geometry, but remember that sp2 orbitals, we have this one kind of pointing out in a plane. We get our lone pairs there. If we want to interact that with a pi orbital, a p orbital nearby to make a pi bond, we have no way of doing that. We've got a vertical p orbital on the next carbon, and we have this sp2 orbital pointing away from the molecule. There's absolutely no way those can interact together. So let's see. So imagine we've got this thing here, and then we've got like this thing here. We need them to overlap. How are they going to overlap? There's no way. So we can't overlap them. And so we can't end up resonating this in. So we don't count this. This lone pair is not part of the pi system. And so that means we still have 6 pi electrons from the 3 double bonds. We've got our 3 double bonds. And as a result, this will still be aromatic. So we might think, okay, well, we've got this lone pair here, but that lone pair can't go in there. So we are only going to count our double bonds. And so we are still going to have an aromatic compound. So we got two reasons why we can't put that lone pair as part of it. If we did, then it would be 8 pi electrons, and then we would have an anti-aromatic system, but we don't, luckily. So that's what you got to do for this. You have to, oh, we're out of time also. I'm just ready to get going. All right, well, I guess that's it for today. We'll continue on talking about this stuff on Wednesday, and we'll go from there. All right, so what's that? I don't think so. I'll have Chamras review with you. I think you have time for that in lab, but in lecture we have to keep going, unfortunately, I think. So I'll see what I can do about finding you some practice exams and stuff too, and I'll throw those on Canvas when I have a sec. So we'll go from there. Okay? Alrighty. Have fun. See you on Wednesday. We'll at least go over what topics you need to learn on Wednesday. So